let's start out talking about electrical power in this set of notes. We've talked about power before, and I know this hopefully will sound familiar to you for that reason. Power, the definition of electric power, or any power, is the rate at which work is done. And for electric power, it's the rate at which work is done by electrical energy. Remember, work is a change in energy. So what we're really talking about is the rate at which energy, electrical energy, is changed from electrical energy into some other form, like light or sound or heat or whatever you want it to change into. Remember, we've talked about before, in any device, and we talked about the lights in the classroom, energy is not really being used in those lights. What's really happening is that the energy is being changed from electrical energy into another form. The rate at which that happens is the power. And light bulb is a really good example to do that, because light bulbs are sold by their power. In the old incandescent light bulbs, we used to have 40-watt bulbs, 60-watt bulbs, 75-watt bulbs. And nowadays you have the curly bulbs, also called CFLs, or compact fluorescent light bulbs, that use less power, that take less power because they don't produce as much heat. And those are like 13 watts, and I think there's a 13 watt and a 20 watt, but you get the point. But remember that we talked about power before, and the equation for power is work divided by time. How much work is done per unit time. We talked about this equation already. Since work is a change in energy, we can simply substitute this in here for work, and we've done this before. I've talked about this already, that power, electrical power, is how much energy is changed per unit time. So power in electrical sense is change in energy divided by time. How much energy is being transferred per unit time. And so an example, again, a light bulb converts electrical energy to heat and light. The question is, how fast does that happen? Other home appliances, anything that you can think about, any electrical appliance, a coffee pot, a hairdryer, computer, TV, whatever you're talking about, all of those are going to convert electrical energy to some other form of energy. Heat, kinetic energy, light energy, sound energy, all those things. All we're doing is saying, how fast is that energy being converted from electric to whatever else. In an electric circuit, power depends on three things. Number one is voltage, the second thing is current, and the third is resistance. Voltage is going to determine the power. The more electricity is piled up, the greater the potential difference, the more power you're going to have. Current also is going to affect it. The greater the current, the faster electrical energy can be converted. And then resistance as well. If you have more resistance in the circuit, that just means electricity will not be flowing as well. Current and resistance actually are indirectly related. The higher the resistance, the lower the current. So if you have high resistance, that means you're not going to be able to have electricity flowing through very much, and the power is going to decrease. All of that is described by this electrical power equation, which is this long thing right here, which in your chart is number 30. P equals IV, which equals I squared times R, which equals V squared over R. All of that is equal to everything else, which means this is another one of these equations that you'll be able to use any two parts. Any two parts of this equation work. P is power, which is measured in watts. I we've had, that's current in amps. V we've had, that's voltage. R we've had, that's resistance, which is in ohms. So the only new one here is power, and really that's not even new because we've talked about it. Again, this is number 30 in your chart. You can use any two of these parts, and there will come times when, depending on what you're given and what you're asked for, you will use any combination of those. We start talking about power. Power gets a little bit more practical to us because your electric bill is charged by power. You may not know a lot about it because your parents probably pay the electric bill, but electric companies charge by the kilowatt hour. A kilowatt hour is really a standard unit of energy. It's a English unit of energy. 1 kilowatt hour is equal to 3,600,000 joules. Right? A joule is really a very small amount of energy. So when your bill comes, it'll tell you the number of kilowatt hours that you used this past month. That's the amount of electrical energy that you used to transfer into other usable forms. Remember, we can't use electrical energy directly. We have to transfer it into other forms like light and heat and sound and things like that. Just as a quick demonstration as to where kilowatt hours comes from, we just wrote this equation not very long ago. Power is change in energy divided by time. If we take this equation and multiply by time on both sides, you get power times time equals energy. Kilowatt hours is a unit of energy. Power is measured in watts, and if you put a kilo on the front, that's 1,000 watts. And time is measured in seconds, and all you got to do is multiply by 3,600 to get hours. So kilowatts times hours, the kilowatt hour is this. Kilowatt hours is power times time. That is energy. So that's how we know that kilowatt hours is a unit of energy. We're not going to talk as much about the kilowatt hour. You just need to know that this is where it comes into play. This is how you can apply it to practical life, to everyday life. But let's move on. Electrical energy now, as we get to the last part of the notes, is measured in joules just like any other form of energy, and you need to write down these two fairly long equations. These are not new equations, like it says. They're just substitutions derived from things that you already know, and if we really wanted to, we could take the time to substitute those. This electrical energy equation, this one here, is number 31 in your chart. And then 32 is actually part of number 29. Number 29, instead of E here, it says U sub E. That's potential energy, but it's still charge times voltage. So all of these are just different ways to calculate energy. When we get to this part of the notes, there's just going to be all it's going to be is recognizing what you're given and what they're asking you for, and then picking an equation out of all of these equations to figure out what's going on. And you're going to be able to use different clues as far as what the problem is about to know where to go to get that equation. All right, let's quickly finish out these notes. You have a few sample problems here that let's see what they look like. First one says, how long will it take a 500-watt coffee pot to warm a pot of water if such a task requires 500,000 joules of energy? And I want you to realize, I know you may read this problem and you don't really have just a really great grasp at even what's going on. You know that there's some sort of coffee pot here and it gives you some numbers and it asks about a time. Don't think about it too much. Just realize, let's just look at it and figure out what they've given us and what they want and find an equation that fits that. So how long will it take? That means they're asking for the time. 500 watts. Hopefully you can figure out that they're giving you the power of the coffee pot here. That's how fast the coffee pot can convert electrical energy into heat energy, because it's going to do that to warm the pot of water. It takes 500,000 joules of energy, this is electrical energy, to do that. It takes energy. So they give us the E, they give us the power, and they want time. So I'm going to look up here and find two parts of this equation that includes E, P, and T, and it happens to be these right here. So E equals power times time, and we're going to simply plug in what they give us. E is 500,000, and that's equal to 500 times time, and if we divide both sides by 500, you will get 1,000 seconds, which is about 16.6 minutes. All right, it's really not that complicated. It's simply deciding what they've given you, knowing what it is, which may take a little bit of practice, and finding an equation that has all the things they've given you and what they want. Take a minute and see if you can run through these problems real quick. Pause the video and then we'll go through them together. All right, with this one, how much current? They're wanting I. If it's plugged into the wall, how much current runs through the pot if it's plugged into the wall, which has a potential difference of 120 volts, right? Now, this is the same coffee pot. I hope that you could figure that out, which means we can still use the power of the coffee pot. And I think we're still going to be able to use the energy if we really needed to. So, but I do know that the coffee pot has a power of 500 watts. The pot is performing the same task, which takes 500 joules of energy. So the amount of energy required here, 500,000 joules, all of those are given to us. And we just found that this task takes 1,000 seconds. That's how long it takes. So I know all these things. So I have V, I have power, I have E, I have time, and I want to know I. Let's try and find an equation that has all those things in it. It doesn't necessarily have to have every single one, though. And if you look, we could use E equals VIT. That has the things that we're given and what we're looking for. Remember, we're looking for current here. And we have energy, we have voltage, and we have time. By the way, that's not the only thing you could do. We could also use E equals PT again, because we have power and we have time. There's a number of different ways to do this. So let's just do E equals VIT just because it's a different equation, and I can show you that you'll get the same thing. If you want to do both of them, try it and you'll get the same answer. E equals VIT here, and we can just plug in what we now know. The energy is 500,000. The voltage is 120 volts. That's the voltage of a normal wall outlet. Current is I, and time is 1,000 seconds. 120 times 1,000 is 120,000, and if you divide by 120,000 on both sides, you would get a current of 4.2 amps. Remember, amps is the unit for current. Again, starts out kind of funky, but once you realize that this coffee pot is the same coffee pot and it's performing the same job, you have the values, you look in the equation to see what you have and what you're looking for, and plug it into the equation. Here's another problem. Your hair dryer uses 120 volts, that's the voltage, while pulling 10 amps I of current. It takes 5 minutes, that's the time, and when you see 5 minutes, you should know to convert, which is times 60 to convert from minutes to seconds, and 5 times 60 happens to be 300 seconds. Takes that long to dry your hair. How much total energy is used? All right, so we have voltage, we have current, we have time, and we want energy. And we look up there to find an equation, and once again, it's going to be E equals VIT. That's the one equation that has all that stuff in it. So we want to know energy. We plug in 120 for the voltage, 10 for the current, 300 for the time. Multiplying all that stuff out gives us 360,000, and the units for energy are joules, and that's what we should have gotten there. Last but not least, last part of the notes, we're going to run through this pretty quickly. You just need to know these terms, but there's not a whole lot more we're going to say about these. We're not really even going to use these in a lab. An electric circuit can be tested with a multimeter. A multimeter is a multi-functioning tool. This is a picture of a multimeter here. You can see this dial in the middle that, if you look closely at a real one, there are many functions, multiple functions that this meter can use. It can measure resistance, it can measure current, it can measure power, it can measure whether a circuit is complete or not. Multimeter can do a lot of different things. These are going to be very specific. An ammeter tests current, and that makes sense because current is measured in amps, so we call that an ammeter. In order for that to happen, the leads must be across an open switch. The reason why the switch has to be open is because the current actually has to go through the device. If the switch is closed, the current goes through the switch and not the device, and the device can't read it. We'll talk about that later when we get to these. Voltmeter tests voltage. That just talks about how much voltage is going from one place to another, or the difference in potential, rather, from the positive side to the negative side. To do that, the switch has to be closed to get an accurate reading. And I've said this before, but AAA, AA batteries, C batteries, D batteries, all of those are 1.5 volts, all of them. But the main thing we need to know is about multimeters, ammeters, and voltmeters in this section of notes. All right, so that completes the notes. on electric current, power, and energy.